Our virtual event today is Rebooting Computing. Our panel of experts will share with you their perspectives on various aspects of the innovations in this area. These include competitions challenging the performers to outdo one another in the best performance at the lowest energy consumption, road mapping of all the relevant technology in a comprehensive manner that captures all elements of computing, quantum computing activities, as well as focus programs and opportunities from major funding agencies in the United States. Our moderator for today's session is Ellie Track, CEO of Envisix, LLC, a company focused on innovative, high-efficiency solar cells. Ellie also continues his lifelong work in superconducting electronics and its applications in communications and computation, including high-efficiency implementation of high-performance computers, as well as quantum computing. If you would like to post about this event on Facebook, please use the hashtag #HKNexperience. At this time, I'd like to hand it over to Ellie Track. Ellie?
Hello. This session is a panel session about rebooting computing, the future of computing, which we always want to grow exponentially because of the need for more complex calculations for a variety of applications, whether prediction, developing of new medication, etc. We have a very distinguished panel with us today. I am Ellie Track. I am with the IEEE, and my day job involves both solar cells and superconductivity. The panel, in the sequence in which they will appear, include Professor Tom Conti from Georgia Tech, who has been one of the leaders in advanced computing architectures, Dr. Paolo Gargini, who's a life fellow of the IEEE. He has a distinguished career going back to Intel for many decades, and he's the initiator of a roadmap for semiconductors, which has now become a roadmap for all electronic technologies for computing applications. We have Professor Youngsung Lu, who was an early contributor to rebooting computing and came up with a remarkable challenge of having image recognition at the lowest power possible, and he will tell you all about that. We have Mr. Bruce Kramer, who is a past president of the IEEE Standards Association and also has had a distinguished career in the semiconductor industry, who will talk to you about quantum computing, an exciting new field. And finally, we have Scott Holmes, who's a former DARPA program manager and also a very distinguished scientist who contributed early in his career and now acts more in the program management and scientific engineering expert frame, who will tell you about DARPA and IARPA programs in this field. So looking forward to it. We can get started with our first panelist, who will give you some comments, followed by the others, and at the end we'll have a question and answer session. So without further ado, Professor Tom Conti.
Hi, I'm Professor Tom Conti of the Schools of Computer Science and Electrical and Computer Engineering at Georgia Tech. And I run a center that looks at post-more computing. And I'm going to talk about some issues that you might think about as you try to plan your career in the future for this coming post-more era. First, let's talk about what this means. Post-more is perhaps a misnomer, and Paolo Gargini will talk about that. What I want to talk about is non-conventional computing. So what is conventional computing? Well, conventional computing is something based on a report, a proposal really, by John von Neumann. It was published, if you look here, in June 30th of 1945. And so it's just about 75 years old. And what John was talking about was a way to implement Alan Turing's proposal for how a computer should work. A couple of things here. Note that it says first draft, and that's true. John von Neumann never got around to writing a second draft. This makes me wonder what computing would be like if he were able to go back and think about some of his mistakes. Nevertheless, the stored program computer, which was motivated by an idea of removing the patch cables needed in ENIAC, has become the standard for how we build computing. It hasn't always been built out of transistors. It hasn't always been built using ICs, integrated circuits. It hasn't always been built using complementary metal oxide semiconductors. So computing has survived many different technological changes, and computing will continue to survive many technological changes as time goes on. For the last 30 years, perhaps 35 or 40 years, depending on how far back you go, CMOS technology has really dominated, which has given us an unusual stable point in the history of computing. But things are going to change now. And you'll hear a lot about the end of Moore's Law, or Moore's Law hasn't ended, or Moore's Law has already ended. And it's a little bit like climate change. Climate change isn't happening. Climate change is happening, and it's already too late. All of that, though, doesn't matter. What matters is there's a hurricane coming, and the hurricane has our name on it. We have to figure out fundamentally different ways to compute outside of the model that John von Neumann proposed. And these perhaps have a potential to surpass classical computers for certain algorithms. There's a couple of qualifiers there. One is the potential. The potential is unrealized today. We know we're going to need thousands of reliable qubits to do things such as Shor's algorithm. However, we don't have those yet. We have to figure out how to construct those and how to construct error-free, or at least reasonably error-free qubits that hang around long enough. The next is for certain algorithms. You should understand quantum computers aren't a replacement for existing computers. You're not going to run Microsoft Word on a quantum computer. Quantum computers are specialized devices used for solving some problems really, really well. And the problems they solve are going to be deal breakers for example, cryptography or communications. And so that's why they're so important. Now, it's an exciting field, and it's rapidly expanding. How can you get involved? Well, understand that quantum started with physicists. In fact, the first proposal came from a physicist, Richard Feynman at Caltech, who said, hey, you know, instead of simulating quantum physics on classical computers, why don't we simulate quantum on quantum computers? That's what today we call analog quantum computers. But by and large, the larger view of quantum computing has evolved over time. And what hasn't evolved, though, is how you design these. If you talk to physicists, they'll tell you that they got it to work. That's what they care about. We got it to work. A couple of examples of that. I had friends in graduate school who were physicists, and I would walk into their lab, and there were pipes and wires going everywhere. And they didn't really care about the efficiency. They were trying to record the result. If you look at the early integrated circuits, each and every transistor was connected by taking a lead outside of the integrated circuit, coming around and going back in. It didn't make much sense. If you think about penicillin, the first way they started making penicillin was to have 10,000 petri dishes with moldy bread. So we've learned a lot since then. What we've learned is how to engineer these systems so that they're efficient. And so if you want to know what to work on in quantum, yes, learn everything you can about the theory, learn about the algorithms, but it's that gap in between that really needs engineers to fill from the theory on up to the algorithms with all the practical layers that will make that translation efficient. So Here you have, for example, a quantum chip. It's a cryogenic chip, and here above it are some wires showing the chandelier that you've already seen. And each and every one of those is going into that chip and coming back out, going down to millikelvin and coming back out. So we have to do the control instead thermally close to the quantum. That involves building computers that can operate at maybe not millikelvin, but 4 Kelvin, where superconducting is a viable alternative to regular ways of building logic. So even conventional computers that work in a technology such as Josephson junctions are going to be things that are going to be exciting, related to quantum, but still support technology for quantum. So what you need to do is think about what are all the things needed in that ecosystem, and how do I, as an engineer, make those things work. Remember what engineers do, make things work the most efficient way possible. Another way of doing computing that is non-von Neumann is analog computing. Now, here I have something you all should be familiar with, which is an op-amp circuit. Now, you can make an op-amp circuit as an integrator, for example, or a differentiator. You can do these circuits and then wire them together to, in essence, implement a differential equation. And then you can sit there with voltage meters and measure the voltage coming out and use that to solve differential equations. That was done prior to the advancement of digital computing. Now, analog computers, though, have problems. The problems they have are error. The amount of error you get is proportional to your, or actually inversely proportional to your signal-to-noise ratio. So how good is your signal? That's a problem. But the thing that they do well is that they can calculate things very fast using physical phenomena that, when we turn them into numbers and we crunch them on a computer, are incredibly inefficient and not exactly rapid. So analog, or let's call it analogous computing, is another area that you should think about. This is an important area that's just emerging. And this includes, for example, open system thermodynamics. We know that open system thermodynamics, because of the Earth we're on, optimize naturally. So if you add energy to an open system, it will optimize and produce optimal results. Optimization is one of the most important problems that we have computers solve today. Similarly, DNA and RNA can be used for computation. We've used DNA successfully for storage of an incredible amount, terabytes upon terabytes of data, using just DNA sequencing. RNA gives us the ability to do computation as well, to do search, for example. And that involves, though, learning enough about not only chemistry, but microbiology and molecular biology in order to apply those ideas to computing problems. Another example is coupled oscillators. Coupled oscillators, we know, can also do optimization. And there are more than just coupled oscillators. You can go on and on with different physical phenomena that solve a problem that we want to solve in the real world. Another example is a lens. A lens is a great way to do a very, very fast Fourier transform. We know that. And it's computationally very, very efficient. Nature will take a collection of salt molecules in a fluid, and slowly, as that fluid evaporates and it condenses, it'll produce a salt molecule, which is the lowest energy state of a combination of different salt molecules. Each one of those, that salt crystal, each one of those, if I tried to assemble that using a conventional computer, would be an NP-complete problem and take eons to solve. So nature has figured this out. Let's go back and look at natural processes and use those to compute. Now, what does that mean for you? It means a couple of things. First, Moore's law is changing. I have a colleague who is a former architect at Intel, and he has said several times that Moore's law will continue. They'll just continue to give us transistors that we can't use any better. So we will continue to get more and more transistors, but we need to figure out how to use them differently. Computing differently has huge potential. Quantum is one, but also analogous computing is another. And each of these areas requires generalists. So my one message to you is simply, if you want to work in this emerging field that's coming, be prepared to learn something outside your comfort zone. Be prepared to be a generalist. Be prepared to be a chemist. Be prepared to be a physicist. Each one of these areas that we're talking about today requires pioneers, and it's your generation that really will bring us into the next generation of computing, and it'll look very different from the last 35 years. Thank you.
Good day, HKN members. Today we're going to review how to deal with the challenges facing any industry every 25 years. This is my 50th year in the electronics industry, and I would like to give you a few clues on how to prepare to successfully manage the ups and downs of industry cycle. Most people rely very heavily on historical trends to make any predictions and consequently generate plans about future steps and action to be taken in their industry. As a result, they are caught completely unprepared by inflection points that unmistakably happen. Nevertheless, people somehow manage to move forward, even though both performance and cost proceed at values much below historical trends. This behavior can be easily understood by considering the typical professional's careers spanning about 30 to 35 years, and you can see from this slide. Therefore, only once in their lifetime will most professionals be faced with these events completely unpredictable for them. This slide depicts how a long-range roadmap can anticipate inflection points and trigger corrective actions to overcome them. Gordon Moore, co-founder of both Fairchild Semiconductors in 1957 and Intel Corporation in 1968, pioneered the method of using a roadmap to make future forecasts, identify problems, and timely trigger research and development corrective actions. In 1965, he predicted that the number of transistors per die would double every year, and this trend would continue until 1975. However, specified action needed to be taken from then on to avoid any future problems. By 1975, data showed his predictions to be correct, and while bipolar devices, highlighted in red, encountered their expected demise for consumers' application, a new generation of MOS devices, highlighted in blue, timely replaced them, avoiding a major electronics industry crisis. He then predicted that the number of transistors would double every 2 years for the foreseeable future. For the following 25 years, the semiconductor industry powered the growth of the electronic industry, running on the shoulder of these three giants that provided the foundation of system architecture, technology, and paved the yellow brick road leading to enhanced performance from one technology generation to the next. The electronic industry continued for 25 years to create smaller devices that were also faster and continuously cheaper. Following Gordon Moore's demonstrated success of the roadmap methodology, the National Technology Roadmap for Semiconductor was formed in 1991. The roadmap became international in 1998, and beginning with 2016, the scope of the roadmap was extended to also include system trends. You can download the 13 chapters of the 2020 IRDS for free at this address. Last slide gives you an example of a very high-level view of the challenges action the electronic industry is facing in the next 5 years. So thank you for your attention, and let's discuss some more during the panel.
We created the IEEE Low Power Computer Vision Challenge because we wanted to encourage innovations in efficient artificial intelligence. Computer vision is this technology that allows computer programs to understand images and videos. And lots of applications need efficient computer vision because those systems run on batteries. So for example, if you're using your phone to take photos or videos, it would be great if your phone could run computer vision tasks, say recognizing your friends in a photo or understanding your videos. But that computer vision needs to stay efficient and not drain the battery too quickly.
The Low Power Computer Vision Challenge started in 2015 at the Design Automation Conference. Tsinghua University took first place in 2015. Then, in 2017, the challenge moved to the International Conference on Computer Vision and Pattern Recognition. Teams come from all over the world to compete, representing the United States, Canada, South Korea, China, Taiwan, and Russia. Winners were an equally diverse mix of universities and companies, including Amazon, ByteDance, Baidu, Qualcomm, MIT, Seoul National University, and the Chinese Academy of Science.
Low-power computer vision is very crucial for mobile AI, but it's very challenging due to the high demand of computational resource and also human resource to tune the models for different mobile platforms that are power constrained. We propose the once-for-all network and AutoML approach that can reduce the computation, memory, and human efforts, automatically designing small and compact models for diverse mobile platforms. It won 3 rounds of low-power computer vision challenges hosted at ICCV, NeurIPS, and CVPR, including the CPU track, DSP track, and also the FPGA track. We thank IEEE, Purdue University, Xilinx, and Google for organizing the competition. We have open-sourced the once-for-all network at ofa.mit.edu. We encourage everyone to participate in the competition.
Since 2018, contestants can submit their solutions online. In 2019, this became an online-only challenge, and in 2020, 46 teams submitted 378 solutions in 4 tracks over the 1-month competition. Each solution is evaluated by the accuracy as well as the energy consumption.
Here's how the competition works. A participating team submits their solution online, then the solution is validated. Finally, the solution is sent to an automated referee system. The system evaluates the accuracy, measures the execution time, and the energy consumption. The final score is the accuracy divided by the energy. To win the challenge, a solution has to be accurate and consume less energy.
Reproducibility is an essential component of the challenge. This challenge is different than just publishing a typical paper. Winners' solutions have to be open-sourced and validated for reproducibility.
Our winner solutions have been presented in many conferences, including the International Conference on Computer Vision and Pattern Recognition, IEEE's International Conference on Artificial Intelligence Circuits and Systems, the Design, Automation, and Test Conference in Europe, and the International Conference on Computer Vision.
Since 2015, IEEE Rebooting Computing provides administrative and financial support. The challenge has received generous support from many sponsors, including NVIDIA, Google, Facebook, PyTorch, MediaTek, Xilinx, Eland Microelectronics, National Science Foundation, and multiple societies in IEEE.
Since 2020, a new track has been added for processing drone video. The problem is to recognize English letters and numbers in the video taken by the drone. Future challenges may include more complex problems, like tracking multiple moving objects when people play soccer.
Low-power computer vision is important for many scenarios beyond drones. The list goes on. Low-power computer vision can be used in many other places, such as wearable cameras, or cameras powered by renewable energy for wildlife observation.
We look forward to making computer vision more energy efficient, so that the technologies can be used in drones, edge devices, or the Internet of Things.
All right. Welcome to everyone from the Eta Kappa Nu group who has joined us here for our presentations on rebooting computing. My name is Bruce Kramer, and I'm going to be talking about one segment of the computing activities that is related to the quantum world. So the first slide indicates that the best that I can do here today is only touch at the very top of a very large subject. So using the traditional paradigm of the iceberg. The first slide really indicates that where we are today, which we'll be talking about in the following slides, is based on a lot of work that's occurred over the last 120 years. And for those of you that are physics majors, you'll obviously recognize the names that have been involved. Shown at the top, in the period from 1900 to 1940, there was a tremendous amount of work in defining and agreeing that quantum physics and quantum mechanics was actually a viable science space. There was quite a bit of additional development in the theory of quantum computing and the use of quantum mechanics from 40 to 80, and there was a triggering event, an aha moment that came in particular from Richard Feynman that motivated a large group of people to actually go off and figure out how they might create a practical quantum computer. And then, of course, there's been a lot of extension of the theories to include sensors and other elements that I'll talk about in a couple of minutes, which is now generally defined as quantum information science. So what has all of this actually resulted in that we can talk about today? Well, one of the indications of relative success is that there has been a tremendous amount of investment. And that's indicated by the patents, the number of new companies started, by national priority, large investments from the national governments, and also an increase in the amount of activity within education. And I'm mentioning here at the very bottom, there are about 200 universities that are now conducting research in quantum computing. And there's a fairly large segment of those that are actually providing master's degrees or potentially PhDs. More interestingly, what I've highlighted at the very bottom is that at least in the US, there's a very strong interest in trying to provide education on quantum to younger students, potentially at the kindergarten level, but obviously in the K through 12 range, which would include high schools. All right, so what do we see here in terms of quantum information science? Computing is a common term, and I tend to use it as a catch-all myself. But you have to recognize that there are sensors and metrology interests that are shown, again, to you on the screen. Communication interests, the quantum internet, quantum cryptography, chemistry, being able to synthesize new materials, and both inorganic and organic. And in the general field of computing, a recognition that there needs to be a fundamentally different way of programming a quantum computer than there is for a classic computer, although the input device is still classic. All right, so I also wanted to highlight for those of you that are not physics majors that we're dealing with a relatively strange world here. And so the terminology, the vocabulary is sufficiently or coincidentally different as well. And I'm not going to go through a lot of explanations, but just to hit a couple of interesting bits here. The qubit is a fundamental bit in the quantum computing arena, and it has a formal definition, which is based on probability theory. There's entanglement, which Einstein in particular called spooky action at a distance, where particles actually correlate over large distances. There's quantum supremacy, which is mentioned, which is being able to prove that a quantum computer can solve a problem that a classical computer really cannot. And then cryptography, which has been one of the motivations for pursuing quantum computing, because Shor in 1994 demonstrated, at least via an algorithm, that he could factor large prime numbers in a very short period of time, and that threatened the RSA encryption mechanism. So there are post-quantum encryption activities as well as factoring activities going on. In the quantum science and engineering area, again, there's a tremendous number of different disciplines that are involved in either the sensors or in the computing or the communication domains. And at the risk of burning too much time, I'll let you read through the various subjects for which there is research needed and research opportunities and engineering needed to make practical computers and practical sensors. All right. Now, because the computer is a common point of interest, I wanted to spend just a couple minutes talking about this. On the far left is a diagram, a schematic of what a quantum computer looks like. And I've blown out the subsequent stages here to indicate that the schematic on the left, that's shown in blue, actually translates specifically into the gray picture at the top middle, which is again from IBM. And that shows the lab environment that a real quantum computer is actually running in. If you drop down, you'll see what the dilution refrigerator looks like. A highlight of that is shown in the upper right, and at the very bottom is an actual depiction of the qubit chip, which is contained in that refrigerator. So there's a lot of hierarchy and a lot of complexity involved in actually building a quantum computer, and reducing this in size and complexity is one of the great challenges in quantum computing. One of the points that I wanted to make is that the IEEE, amongst a large number of other organizations, is collecting and disseminating information on quantum information sciences. And an indication of what the IEEE is doing is shown on this page, where we have in fact started standards in this area. There are juried publications available, a large number of white papers and reports that have been published. And if you go through the Explore database, you'll find almost 13,000 articles, peer-reviewed articles on quantum computing. And within the IEEE Spectrum magazine, which is widely disseminated around the world, there are 768 articles that have appeared in Spectrum. We have a quantum initiative, which is largely responsible for the activity shown on the left. And that was a spin-out from discussions and obvious interest we had within the rebooting computing community. It does have its own presence, its own website, which is shown on screen. And lastly, we have created a very large event called Quantum Week, which is going to contain 270 hours of material from tutorials, birds of a feather, workshops, keynote presentations, and technical presentations. The videos for this will be available through November 30th of this year. Lastly, I wanted to highlight that because this is a popular talk, it seems like everyone wants to get involved, and even Dilbert has found some time to comment on both the promise and the reality of quantum computing. At this point, however, I want to stop and thank you for letting me bend your imagination for a few minutes. And I hope that you're interested in further exploring the quantum information sciences aspect. And with that, thank you.
Hello, this is Dr. Scott Holmes, and I'm going to be talking a little bit about my career, or what I'm doing currently in my career, which is later stage management more, and I call it playing fantasy football for real. Okay, I've worked at several government advanced research project organizations. Most famous one is DARPA, and you might have heard about that and wondered, what's the hype about? What's going on there? I also work at IARPA, which supports intelligence community, and there are others like ARPA-E for advanced energy projects. So to give you one flavor of what a program is like, at DARPA, there was a DARPA Grand Challenge in 2004, autonomous ground vehicles, and the challenge was build an autonomous ground vehicle that goes from one point in the desert to across the Mojave Desert to another point, and a 150-mile route, and it just has to be an autonomous vehicle with a $1 million prize. Okay, so they started and sent these vehicles off, and they had several vehicles involved, and they all stopped. They all crashed. Or crashed, stopped, ran, the variety of things. The furthest one went about 12 kilometers out of their 240-kilometer route. So they didn't get very far that first year. The second year, there were several finishers, and things have gone on from there to the point where today we're much closer to having truly autonomous vehicles. This was an example of DARPA back in the early 2000s saying, this is something we need. They weren't getting enough interest and excitement, new ideas, and so they created a challenge to do that. So I'm going to talk a little bit more about, in general, how do our ARPA-style programs do this? And I say it's like fantasy sports, but for real. Fantasy sports, okay, you start with a game, you pick teams, you play, you have a winner. I would assume that most of you know about or have experienced fantasy sports. What we do at the ARPA style, what I call the pro version, is that first we have to create a game. And to do that, we back up and we say, what is the need? Back in the early 2000s, they were looking at autonomous vehicles. I work in the area of advanced computing. One of the needs that we've had is for more energy efficient computing. Currently, there are data centers that are getting really big, and they're taking tens of megawatts to run these things. 100 megawatts in some cases, and that's just too big. It doesn't scale well. And we need to create something else. So we have a need. So we look at, okay, what's this need? How do we get to the core thing? How do we get the innovation and make it, you don't want to be building a complete data center to prove that you've got a more energy efficient computing style. You start much smaller. And there's a variety of ways that you can go about that, and you think about the concepts, and then you start to narrow them down. Along the way, you create rules, and you also have to create referees. For example, with the energy efficient computing, we had computations that were on the order of 1 attojoule per computation. And 1 attojoule is 10 to the minus 18 joules. It's very hard to measure that. So we had to create our own ways, our own referees for measuring those kinds of extremely low energies. Then once you've got a game, then you can go out and you can pick your teams. Who's going to compete in this? And now in fantasy sports, you pick a team and they automatically play together. That's not true in the real world. Sometimes you have to get in there, coach them, help them form teams. Then they play, and then sometimes we have to change the rules because the game goes along a little while and you say, that's not quite right. And then you have to change the rules. And then we come to a winner. So this is just to give you some sense of how it is or what's going on at places like DARPA that run these things to try to develop new technologies. Early in careers, sometimes people will be on the teams that are actually trying to do a DARPA project. And I'm now at my late stage career where I'm running these games. So, thank you.
Okay, well, that was a whirlwind tour of the future of computing, including lots of exciting things, the competition, quantum computing, and so on. Let's see if we don't yet have any. Okay, here's one question. I have 2 BA degrees in physics and electrical engineering, but it's hard to find a position with my degree. Can you give me some resources to look for jobs? Wow. Bruce, you want to take that on? You came from the industry.
Yeah. Obviously, there are recruiting or job placement activities all around the world, so maybe not a new subject. If the question is, how can I find a job in rebooting computing, then that's, of course, a little bit different question. Just to use an example, I'll use one example here, because I was talking about quantum computing. There are job listings on quantum computing sites who are looking for people to join the quantum computing workforce. How that matches with anyone's individual interest or degrees, knowledge base, of course, is beyond my knowledge. So, not too much I can do just by talking on the phone here. I can't give you a URL. But there are a considerable number of job postings that I'm aware of in the quantum computing world because they show up on my desk every day.
Okay, thank you. Yeah, Bruce, that's very good. Thank you. And so I guess one piece of advice is look for things in quantum computing. They need help at all levels, from the technician all the way to the complete expert, etc. That's an exploding field. So let me ask Young-Sang a question. Young-Sang, you talked about the competition for image recognition and at the lowest possible power. And as I understand it, it's been going on for many years, and the performance has been improving year after year, and you're now turning to computer vision, which basically includes video. Can you say a few words about how that can be applied, and I know you're looking at that, for recognizing issues in disaster areas, for example, and what projects might be in the future to actually apply this technology?
Okay, thank you. Yes, so we started from recognizing objects in images. Can you hear me?
Yeah.
Hello? Okay, thank you. Now we have moved into recognizing activities in video starting from this year. In the future, we hope this technology can be applied in fully autonomous systems such as UAV or called drones, maybe in disaster management. So imagine maybe there is a disaster, we can launch dozens or hundreds of drones and they can tell where people need help. The technology is not here yet. We still need to develop a lot of technology to make that possible. One of the challenge, as you mentioned, is the energy consumption for this very complex computation. We humans can do very complex computation very efficiently, but computers still cannot. So in the near future, we will keep pushing challenge forward. We have started talking about something much, much harder to really push the technology forward.
Okay, thank you very much, Young-Sang. Here's a question for Professor Conti related to education. So, Professor Conti, you talked about quantum, and of course Bruce also talked about it, but folks are wondering, to be able to understand quantum computing, there seems to be lots of prerequisite requirements, understanding quantum mechanics and all that stuff. Is there an approach where somebody without that level of expertise can begin to get involved in one or more aspects, whether it be algorithm or hardware or anything else? how is the academic community thinking about preparing the younger generation to be active in this field?
That's a great question, and it is true that at least today, if what you want to know, if what you want to do is quantum, you need to investigate and learn a bunch of physics. But let's step back. The first integrated circuits were really designed by physicists, and they were designed by solving fairly complex physics problems. And then later on, due to, for example, Carver Mead and Lynn Conway, we came up with design rules that if you followed these rules, then you would end up satisfying the physics and then able to design a much, much bigger system. And that's how we design integrated circuits today, using design rules like that. So there will be a set of design rules for physics coming forward. There are several textbooks that are just now emerging that teach quantum at the level that you need to understand in order to be competent in quantum computing. Unfortunately, those courses are just rolling out now. We have one at Georgia Tech, for example, that doesn't really emphasize too much of the physics. It really only requires that you come in with knowledge of linear algebra, you learn the rules of the game, and then you can start reasoning about the algorithms after you learn the rules of the game. And so that level of understanding of quantum is coming. There are textbooks that are emerging, and you know, look at your current university, or perhaps if you're looking at graduate school, potential graduate school that has a reputation in quantum, if you're interested in going there. But when I say a reputation in quantum, let me be specific. One in quantum computing as opposed to quantum physics. You want somewhere where someone in the CS or ECE department is doing research in how to do quantum computing, because those are the people who can teach you that easier to access level of abstraction that you can use then to be proficient in the field.
That's excellent. Thank you very much, Tom. Bruce, just building up on what Tom has said, I know, Bruce, you've been involved in the educational aspect of the quantum initiative from IEEE. And maybe you have a broader view of what other universities across the board and what IEEE maybe is planning to do. Can you add to that as to what's in store in the future of preparing those simpler courses to allow a broader constituency to participate in development of quantum computing?
I'll try to complement what Tom said, which is correct and logical, and that is that what we have seen from within the quantum computing industry is not just a need for PhDs in quantum physics or quantum computing, a whole ecosystem of people that are knowledgeable about what quantum computing is and quantum sciences, again, all of the other aspects, because it's different. And what that has led us to understand is that we need not just PhDs, but master's students, undergraduates, high school students, and even elementary school students to have some understanding of what's going on that's different in the quantum world. And you know, the switch from classical mechanics to quantum mechanics is a substantial one, and it has not traditionally been taught at the lower levels. And so building that pipeline of understanding, again, as Tom is suggesting, a minimal amount of physics, certainly at the lower levels, and a minimal amount of math, finding some way to convey the concepts that are fundamental and different is an interesting challenge. One of the things that we're seeing is that vast majority of people who will enter the quantum computing or quantum information sciences workforce not trained as PhD quantum physicists, from other disciplines, adding to their knowledge base some additional aspects that are useful in the quantum arena. The last comment I wanted to make is that the complexity, ultimately the complexity of the quantum field is being attacked. We're trying to reduce the complexity into bite-sized chunks so that it can be digested at lower levels of education, right? And an example is that IBM components of actually put an application into Apple Play. It's called Hello Quantum. And it doesn't tell you how to build a quantum computer, but it gives you some feeling for the operators that are used in quantum computing. And it's also been called a marble game. But driving the complexity down into components that are easily understandable has been a big challenge. That's part of what our education group within the quantum initiative is trying to do, is to find ways to break the complexity down and distribute it as widely as possible so that we're not teaching 100 PhD students, but we're teaching 100,000 high school students. Haley?
Okay, thank you very much. Thank you very much, Bruce. I have a question for Scott here. Scott, you indicated that you're involved in management and so different kind of perspective on science. And there may be engineers who are graduating or have graduated a few years ago who are not necessarily interested in being benchtop engineers or making things, but are interested in things like policy, interested in program management, etc. So for those folks, what is the recommended path? Should they join a consulting company? Should they maybe become staff for the congressman or senator in the science area? You probably have the most experience of anyone here in this group to maybe give some perspective as to what one does if that's the inclination they have.
Well, yes, there are other paths. A traditional path is to start as an engineer, but then to look for other opportunities. There are some direct paths, for instance, in consulting, where there are companies that provide services to the government, for instance, and so you can get in and get involved in seeing what the policy is, or helping organizations like DARPA and IARPA to do what they do. So there are other opportunities. I just wanted to make the point also that there's been a lot of talk so far about quantum computing and quantum information sciences, but this is a more general thing, that there's a huge variety of needs. There's neuromorphic computing, for instance, brain-like computing. There's new approaches, new devices, new materials. This is a period in which there's a lot of exploration. And so it's some of what you hear about quantum computing or the quantum field applies, but there's a lot of opportunities out there in a variety of different fields.
Very good. Thank you so much, Scott. Paulo, I have a question here which would seem to be open-ended, but you've been in this field for a long time, and people sort of, in casual conversations, they hear about Moore's Law is ending, Moore's Law is ending, and they really want to find out, is it really ending or not? And if possible, can you sort of give like a concise explanation of what the situation is? Maybe some parts of it are ending, some parts are not, etc. Maybe you can speak to that a little bit. So the question that came is as follows, Paulo. It says, is it accurate to say that Moore's Law is running out or coming to an end?
Thank you, Elliot. Can you hear me?
Yes.
Oh, okay. So, as I explained in my presentation, Moore's Law was first formulated in 1965, a long time ago. And it actually explained many elements that were necessary to keep the Moore's Law going. But, one of the elements, and it was not the only one, consisted in making everything smaller. And therefore, if you reduce the size by 30%, the area goes down to 50%. And so you can double the number of transistors by simply doing a shrink of all the dimensions. And as long as the law of physics holds,
that is a very simple approach. And what happened from 1975 to approximately 2000, 2002, everybody did that. So imagine many engineers, that were coming into the field, that's the only thing they knew. And so they confuse Moore's law with doing scaling. That is an important ingredient, but it's not the only ingredient. And so when in the 2003, 2004, the methodology to increase the number of transistors changed, relying on the transistor architecture, making it partially vertical and so forth, many people thought that since it was not just scaling, that the Moore's law was coming to an end. But one by one, we have activated multiple elements of Moore's law that will continue until the end of this decade, meaning 2030. But unfortunately, many people knew only one item, especially when you talk to the press. They really can only latch onto a single item. And so every 5 or 10 years, somebody comes up with a surprising article saying Moore's law is coming to an end. But we don't see any end until the end of 2029, 2030. But even so, it's not the end, because we're counting from our friends from the quantum world to be able to store multiple bits in a single location. And in that case, we can simply replace Moore's law with saying the number of transistors will double every year, by simply saying of 2 years that the functionality will double every 2 years. And so in this respect, the concept and the spirit of Moore's law is never going to end.
So if I were testifying in Congress and my congressman or senator pushed me and said, this is a yes or no answer, is it ending or not? I guess what you're saying is you can't say yes or no. It's both yes and no, right?
No, aspects that the push, the Moore's law, run out of steam. But Moore's law, Morse identifies 6 elements. So one of these elements will run out of steam in 2030, but not the other 5. So Moore's law will never stop if you change the formulation from the number of transistors doubling every 2 years, the functionality doubling every 2 years. There is no end.
Okay, thank you very much, Pablo, for this nice explanation. We're going to go back to quantum now. There's lots of interest in it, and I have a very interesting question. I'm going to read it because it's well formulated. And the question says the following. From the pictures shown, quantum computers seem very inconvenient in terms of size and complexity. Are there currently forms of quantum computers that would make them actually feasible in other applications that maybe do not have entire rooms dedicated for the computers? So I don't know who wants to tackle that, Professor Conti or Bruce Kramer. Maybe both of you can chime in a little bit. I guess you're our quantum experts here.
Let me just say no. So currently, no is the answer. But Bruce, now that I've given that, if you know of anything that could put quantum in your pocket, you let me know.
Yeah.
But everything I've seen currently is huge.
I have to agree with Tom. That is one of the challenges that, again, going back to the reference to ENIAC, every quantum computer at this point ENIAC sized, not because of the computational unit, which again is chip size, integrated circuit size, because of all the support equipment that surrounds it, including the cooling, which is superconducting. So the other thing is that even the picture of the environment in which a quantum computer lives a little bit misleading, because a quantum computer is really nothing more than a timeshare device at this point. Go into it directly, stuff out of it directly. It's a tremendous amount of translation from the classic world into the quantum world and then back out to the classic. There is, at this point, again, dangerous prediction. there is no expectation to have quantum computers in their home. Fortunately, that prediction had been made also for classic computers, and now we have them. But at the moment, it's very far in the distant future. And a computer would be small enough or cheap enough, even useful enough to warrant being placed in a house. There's a good challenge for our Theta Kappa Nu.
Ali,
Okay,
may I answer?
Please.
So, the first element is you are not looking at the way the quantum computer will be in the correct way. You have to think of a quantum computer like a data center. There will be these places that have quantum computers where the information is synthesized, the algorithms are working, but it will not be in your pocket ever. So the importance is that for two fields that are very popular nowadays, the field of 5G and 6G and the world of quantum computing, by the end of the next decade to come together. There will be quantum computers in very specific locations, and then you'll access them through the internet. And for that, you have to get very short latency times, like 1 millisecond and so forth. If you look at Europe, for instance, in this moment, IBM has a single Watson computer in Germany that serves all of Europe. The quantum computers will be precisely the same. There will be several of them in key locations, but you will access them through a very fast internet.
Thank you very much, Paulo. We've hit the top of the hour. I'm assuming the session ends now. There is one more audience question. I don't want to skip on it. Let me read it, and hopefully somebody can jump in from the panelists and answer it, and then we can close after that. I'm reading the question now. During my 30-year career as an electrical engineer, it has been my experience that the most successful innovators tend to be those who have significant experience in one or more technical areas, as well as more generalist interests, as opposed to those who start as high-level generalists who lack technical depth in these areas. Any thought from the panelists on this? I guess starting as an expert in one technical area, or starting as a generalist, or the combination of both. Scott, maybe you might be the person to start on this one, and we should keep it brief because we need to close soon.
Yes, I agree, and that was what I was kind of getting to as far as usually start in some engineering field, you really get to know things, and then move on, and then move up to a higher level.
Okay, that was a nice and sweet answer. So we're exceeded by 4 minutes our session. I want to, on behalf of all the attendees and all the organizers, I want to thank our panelists. That was really a very exciting presentation of the future of computing, and the discussion session was also nice and lively. So thank you very much, and we close the session now.